Okay, so 3.7, we're taking a look at solving equations, or solving systems of equations graphically. So remember from Algebra 1, a system is when you're solving for two or more variables. All the problems I give you today will have two. They won't have more than two. And anybody have a guess what we're going to be looking for graphically? If we put, say, we're going to have one equation in y1. We'll have another equation in y2. And what do you think we're going to look for? Where those two equations do what? Yeah? Intersect. That's all we're going to be doing, looking for an intersect. The important thing is when you're solving a system, make sure you solve for every variable. So, say you're solving for an x and a y. You're looking for an intersect. Bailey just said it's an intersect. Well, where they intersect is a coordinate. So one way you can write your answer when you're solving a system with two variables is as an ordered pair. X, comma, y. You need to tell me both numbers. And we already said that. So to solve a system graphically, we're going to calculate the point of intersection. So as far as like the features of the calculator, we're not really learning anything new today. We're really just plugging something in and using a skill we've already done before. Now, you don't have to write the answer as an ordered pair. You could do something like this. You could write x equals y equals. I think that's how I have it set up on Edge Elastic. A box for x and a box for y. All right, so let's think about when we graph something on the calculator. What letter always has to be by itself if you want to type it in on the calculator? Chris?
Y.
The y. So we may have to take an equation and rearrange it a little bit to get y alone before we can put it in. And both of these we do have to rearrange. Can anyone tell me in the top equation, what are the two steps you would have to do to get y alone? Two steps. Sarah?
Subtract 2x from both sides.
Yep.
Divide by 3.
Yes, you'd have to minus the 2x and then divide by 3. So if you did that, you would have, let's see, the 5, let me write this. So minus the 2x and then divide by 3. So minus the 2x. And then divide that by 3. And the 5 would be on the other side, but that's also going to get divided by 3. Okay, any question on how I got y by itself there? I have to do the same thing on the bottom. Anybody tell me my two steps on the bottom one? Ashley?
Add the 3x to the other side and then divide by 5.
Okay, so I'm going to add the 3x, so that's going to become positive. But then I have to divide by 5. The 21 would have stayed right where it is, but it would get divided by 5. Okay, so now we're going to use that on the calculator. Let's put one of them in y1, put the other one in y2. Just got to be careful with all the fractions. I would use parentheses. So let's put in negative 2/3 x plus 5/3. That's how you type in the first one. And the second one, we could put 3/5 x plus 21/5. Let's try zoom 6 and see where we're at. Okay, so there's my first line with a y-intercept of 5/3 and a slope of negative 2/3. There's my second line. And now, what do we have to calculate?
The intercept.
Calculate the intercept. Second, calc, intersect. Enter, enter, enter. And it tells me that they cross when x equals negative 2 and y equals 3. Perfectly fine to write your answer like that, two separate numbers, or if you wanted to write it like this on the homework, that's fine. Any questions on solving that one? Well, that's pretty much all we're doing in this section. This one, read the directions carefully. Is it asking you for the solutions? What is it asking for? Yeah?
It's asking for the amount of solutions there are.
The amount. So you don't have to find what they are, just say how many there are. They're both already solved for y, so all we have to do, type them in. Negative x cubed plus 3x squared. Negative x cubed plus 3x squared plus x minus 3 and negative 2x squared plus 5. Okay, and we're looking for how many solutions there are. Okay, there's my cubic. That was the first one. Second one is going to be an upside down parabola. All right, put that over here. So, what's the answer? How many solutions are there to this system? Yeah? I don't think it's going to be 2. Yeah?
5.
Okay, how'd you get 5?
Just count the number of times we went through the x-axis.
So are we looking for the number of times that we cross the x-axis, or what are we looking for here? Or like, what did we look for in the last one? Think about, what did I calculate to get the answer in the first example? Do you remember what I pressed, Jack?
Intersect?
Intersect. Okay, so what we're looking for here is the intersect, same thing. So we're not looking for roots. So do you have a different thought about how many answers there would be? Besides 2. Jake said 2. Ashley?
Could it be 3?
How'd you get 3?
I don't know. I'm just thinking that it might cross farther down on the graph.
Yeah, it does cross further down on the graph. Just because you can't see it doesn't mean you can ignore it. It is a solution. So if you set your y min, I don't know, try negative 50. We can definitely see 2. Might be a little harder to see now because I'm zooming further down. Actually, I don't think they're going to be that hard to see. So you'll clearly see the first 2. And now, yeah, I think I just barely got it. There is a third one right there. Okay, so the answer to this problem is 3. So the important point is make sure if you're not seeing everything that could be off the screen, zoom out a little bit so you can. Because if you said 2, you wouldn't really get partial credit because it's just not the right number of answers, and there's no work on this problem other than zooming out. Okay. Questions on example 2? All right, let's see. Let's just do this graphically, okay? Because that's kind of what we're focusing on. So let's do the same kind of thing again. Let's type them in. Already solved for y, so that's nice. X cubed minus x and 3x. I'm going to go back to zoom 6. Now remember, before I even look at the graph, a cubic can turn twice. So if you see something like this, or something like this, then you're pretty much seeing everything the graph is going to do. This one is linear. That's just a line with a slope of 3. So it could be either one of these two graphs, but I know the end behavior is down on the left and up on the right because it's an odd positive degree polynomial. So let's look at the graph now. All right, so I'm pretty much seeing everything that's going to happen. How many solutions does it look like there are? Yeah, Chris?
3.
3. So this time it says solve. That means I want to know the solutions. So the answers are, it looks like 0, 0 is an answer. In fact, I can check quickly. If I plug in 0 for x, I get 0 for y. And if I plug in 0 for x, I get 0 for y. So yeah, 0, 0 works. And then I think they are nice answers. 2, that's 2, 6. So if you plug in 2 for x, you will get 6 for y. You can check it. 2 to the third power is 8. 8 minus 2 is 6. Now plug it in here. 3 times 2 is 6. Yeah, so it works. And the other answer, it's kind of symmetrical. -2, -6. That symmetry doesn't always happen. You should do second calc intersect 3 times. I just remembered what the answers were from doing the problem earlier. Okay, any questions on that? All right, so that's 3-7. Calculating basically an intersect for a system. So, last thing we'll look at is 4.1. So we'll do this today, and then 4.2, we're going to split that up into 2 days. So what we're looking at in 4.1 is what are called rational functions. Let me show you. That's an example of a rational function. That's another rational function. A rational function is basically when you have a fraction and you have a polynomial in the top and a polynomial in the bottom. Here's another example. That's a quadratic polynomial. That's a linear polynomial. When you divide them, that's called a rational function. So a rational function is of this form. It's a fraction where the top and the bottom are polynomials, but the bottom can't be 0 because you can't divide by 0. So because we're going to be looking at fractions, we can go back now and talk about domain. You're never allowed to divide by 0. So when they ask you for the domain of a rational function, make sure you never include a value that would cause you to divide by 0. Okay, here's another example of a rational function. I'm not going to do anything with that problem right now, I'm just showing it to you. It's a quadratic polynomial in the top divided by a linear polynomial in the bottom. Here's another example. It's a quadratic in the top and a quadratic in the bottom. And that's it for the examples. Anybody else need to copy anything up there? No. Okay. So when we have to find the domain, basically we're going to be looking for what values make the denominator 0. Sometimes it's simple, like in f of x. You wouldn't want to let x be 3. So the domain is all reals except 3. Sometimes, like in g of x, it's a little bit more complicated. Oh. All right. So again, when we're talking about domain, it's all real values. Okay, we don't have to worry about imaginaries, but it's all real values except the ones that make the denominator 0. So don't plug in any numbers where the denominator could be 0. Okay, oh, I remember what I was saying. So before the sound. Sometimes the denominator, it's a little bit more complicated to figure out what makes it 0. So how are we going to do that if it's a little more complicated? That's what we learned in all of chapter 3. How do you find roots? How do you find numbers that make a polynomial 0? Well, hopefully you won't have to do any more than factoring a quadratic formula. Worst case scenario, you could have a cubic in the bottom, and then you have to use the rational root theorem to find a root, and then use synthetic division. So, that would be kind of the worst thing that could happen. So hopefully it's not that bad. So let's look at this one and see if we can find the domain. So what's the domain of this one? Yeah, Ethan.
Everything except 3.
Yes, we could do it two ways. We could say all reals except 3, or you could write the answer as an interval. And for the test, it is important to know how to write it as an interval. So think of it as a number line. Right? Here's 3. It's like there's a hole at 3. You can include everything below 3. You can include everything above 3. You can't include 3. So how would we write part 1 of that interval? Represent everything below 3. Yep, Tyler?
Less than 3.
So as I'm thinking not as an inequality, but as an interval. So we're going to think about like maybe brackets or parentheses, and we're probably going to have that U symbol. But that would be as an inequality. But I want to take what he just said and write it as an interval. Sarah?
Parentheses, negative, infinity, 3, parentheses.
Yep. So that's part 1. Or how would you write part 2? Part 2 is right here. Yeah, Ashley?
Parentheses 3, comma, infinity.
Yes. And remember, the parenthesis means do not include. If you put a bracket, then that means include. We don't want to include 3. Okay. Questions on that one? So everywhere you have a hole in the graph, it breaks it into another piece. If you had a graph with 2 holes in it, you would break it into 3 pieces. Everything below that, between that, and above that. But this one only had one hole in the graph. Okay, let's look at this one. So we're trying to find all values in the domain. What do you think we should do to the bottom that would make it easier to find the roots? Yeah, let's factor. It's always going to be easier to find the roots if it's factored. Doesn't matter what's in the top. I'm not even going to worry about the top. Francesca, when I factor that, what would be my first term in each set of parentheses? Think about what times what would give you x squared.
What times? Or what times?
Like if I put a 5 and a 2, would 5 times 2 give me x squared?
Well,
No.
Would be X and X?
Yeah, x and x. We're going to start with that. And Matt, what about my signs? Both positive, both negative, or one of each?
One of each.
Yes. The rules here, because you have a positive middle and a negative at the end, we're going to do one of each. Now I need two numbers that multiply to give me 2 and subtract to give me 1. And I just have to make sure I put them in the right spots. So Abigail, do you see what two numbers multiply to give me 2? Say it again.
2 and negative 1.
2 and negative 1. All right, let's try it the way she said it. X squared minus x plus 2. So a minus x plus 2x is a plus x. And 2 times negative 1 is negative 2. All right, so Jack, what would be my domain in this one?
X can't be equal to -2 or +1.
Yeah, all reals except -2 and +1. So this would be more like this case. You could pick anything below -2. Or you could pick anything between -2 and -1. Or you could pick anything above 1. So below -2, between -2 and -1, or bigger than, I'm sorry, let's put that, bigger than 1. Both answers are correct, but again, this is definitely important, this interval notation, for the test. Okay, any questions on that one? Okay, so a little bit harder because you couldn't get the root as easy as example A. Because example A is already factored, there's nothing to factor. Okay, but if it's not factored, factor it first. So both of those functions that I gave you were rational functions, but they were complicated. This is the simplest rational function you can have. 1 over x. You have a polynomial on the top, that's a constant, and you have a linear polynomial on the bottom, just 1x. Let's graph that and see what it looks like. Now, if things start to get really steep on a graph, the calculator gives up. It just doesn't draw anymore. So let's type this in and see what it looks like. And then I may modify it a little to show you what it should really look like. That's pretty good. That's not exactly what it looks like. This part should continue up, and this part should continue down. And this goes. That's called the rational, well, that's called the reciprocal function. Now, I want to look at what happens as x approaches infinity, meaning as x goes further and further and further to the right. And then I want to look at what happens as x approaches negative infinity, as x goes further and further and further to the left. Let's look at our table. Let's start with 10. Go to my table, type in 10. When x is 10, I am at 0.1 for the y-value. Okay. When x is 100, I'm at 0.01. When x is 500, I'm at 0.002. What does it look like I'm getting close to? And I'm going to get close to this number, but I'm never going to reach it. Yep.
0.
0. Because you're taking the number 1 and you're dividing it by x. The bigger the number you divide by, the smaller the fraction you get. But what if I take 1 divided by 1,000,000,000? I mean, that'll be really small. Will that be 0? No. Even if I divide 1 by 20,000,000,000, it's small, but it's still not 0. It never will be 0. And the same thing happens if you go in the negative direction. If you take 1 and divide by negative 1,000, very, very, very small negative number. 1 divided by negative 1,000,000, it's an even smaller negative number, but it's never 0. So, as x approaches infinity, or as it approaches negative infinity, the y value is approaching, never reaching, 0. And I think this was in the title of the section, but does anybody remember what you call that, a value you approach? Like on a graph, you usually put it as a dotted line, something you get very, very close to, but you never actually reach it. You want to remember what that's called? Yeah.
What's the first letter?
An A. Starts with an A. Yep.
Asymptote?
It's an asymptote. So an asymptote is something you get very, very close to and you never reach. In this graph, the horizontal line y equals 0 is an asymptote. Let me put that in. Let me do it as a, you know what, let me make both of these lines thin, because when you're trying to show asymptotes, the thinner you can make it, the better. Thick lines kind of like overlap each other. Alright, so that's as thin as I can make them. So there's 1 over x, and watch what happens when I draw y equals 0. Okay, and I'm going to put this, I'm going to have to make it bigger so you can see it. Let's just take it. What's happening there is the blue and the red line are coming together, but they're never going to reach. Eventually, I'm going to run out of pixels on the screen, and they're going to be right on top of each other. But understand that they never actually, the blue line never reaches 0. It gets close. And we usually, again, show that as a dotted line. I could have made it dotted. I just forgot to. So the way that you find a horizontal asymptote is you look at whatever formula they give you and let x get really big. Plug in a really big number for x and try to look for a pattern. What are you getting closer to? Either plug in a really big positive number or a really big negative number. Remember, anytime you have an x in the bottom of a fraction, if the bottom of a fraction is getting really big, the entire fraction is getting really small. Okay? So again, to find the horizontal asymptote, plug in a really big number for x. These are just different examples of asymptotes. This is a graph that actually crosses the asymptote early on. Then it kind of hits a peak value, and then it just levels off. And it would just keep getting closer and closer. This graph on the left is more like the one we did. It's coming up towards the asymptote. It never crosses it, but it gets closer and closer to it. So a couple examples of asymptotes. All right, let's look at this one. So, find the horizontal asymptote. And when I ask this on the test, I'm going to write it like this. Find the equation of the horizontal asymptote. Find the equation of the horizontal asymptote. All right. So, how do we find the the horizontal asymptote. What did I say to do with x? Remember? What did we say to do with x? Yeah. Yeah, let it approach infinity. So what happens, let's just start with this. What happens to what I circled as x approaches infinity? What does what I circled approach? Tyler?
0.
That part approaches 0. Now what do you get if you take something that approaches 0 and add 2 to it? You're getting a number that's going to approach, yeah? 2. So your horizontal asymptote in this problem is at 2. Since it's horizontal, how do you write the equation of a horizontal line at 2? Yeah.
Y equals 2.
Y equals 2. If this was a multiple choice question, I would definitely put x equals 2 as a choice as well. But when you write x equals, that's vertical. Y equals is horizontal. All right, let's try this one. Anyone think they can tell me my horizontal asymptote in this problem? So as x gets really, really big, what am I going to approach? Yeah, Jake?
-3.
-3. You plug in, say, 1,000,000, you're going to have 1/1,000,000th, which is basically 0, minus 3. So that's going to be like -2.999999999. It's going to be very, very close to -3. That's y equals -3. And if you plugged in like -1,000, you would have -0.001. You'd have -1/1000th minus 3. Well, that's minus 3.001. Very, very, very close to -3. Either a little above it or a little below it. Depends if you plug in a really big positive number or a really big negative number. Okay, so we looked at horizontal asymptotes. That's when you look at what happens as x approaches infinity. Now we're going to look at what happens as x approaches a value that's not in the domain. Like in this one. What number are you not allowed to put in the denominator here? In this one, you don't have to use quadratic formula or factor. This one's pretty simple. Yeah.
1.
You can plug one in.
0.
Yeah, you can't plug in 0. So we know we can't put a 0 in, but what happens if we plug in a number close to 0? Like 0.001. Very, very close to it. So let's look at what happens as we approach the number 0. Now there's two directions you can approach 0 from. 0 is in the middle of a number line. This means to approach 0 from the right, or the positive side. This means to approach 0 from the left, or the negative side. So you might see this abbreviated like this, as x approaches 0 from the positive side. So let's try that. What's a number, I can clear this out. What's a number that's very close to 0, but on the positive side? Then we'll do a number that's close to 0, but on the negative side. Ethan?
1.
Even closer. I want to get very close. Yeah.
.001.
Yeah, 0.001. That's a number that's extremely close to 0, but it's just barely on the positive side. And if I plug that in, I get 1,000 for y. If we go 0.0001, that's even closer. That's 10 times closer. I get a y value of 10,000. What do you think my y value is approaching as I try to plug in a number closer and closer to 0? It's approaching infinity. The smaller you make this value, like if you plug in 0.000001, it's going to be 100, I forget how many zeros I said. It would be very high, it'd be like 100,000. Now, let's write this down first. And then we'll look at what happens as you approach 0 from the negative side. So Abigail, what's a number that's really close to 0, but on the negative side? Negative what? Let's get much closer than that. Negative 0.001, sure. And if we plug that in, negative 0.001, I put an extra one, that's fine. I get negative 10,000. So what do you think is happening as I approach 0 from the negative side? What's my y value approaching? Negative infinity. And that's why when you look at the graph, as you start to approach 0, all of a sudden, that goes straight up and it approaches infinity. As you come at it from this way, all of a sudden you drop off and it goes to negative infinity. So, this says as x approaches 0 from the positive side, y approaches infinity. And as x approaches 0 from the negative side, negative is the left side, we approach negative infinity. This idea of all of a sudden your graph going up to infinity or down to negative infinity is the behavior that always happens at a vertical asymptote. In that graph that looked something like this, we had a horizontal asymptote. I just put that in black. But we also had a vertical. So a vertical asymptote is a line that you get closer and closer to, but it's vertical instead of horizontal. So in general, the way you can tell if a certain number is a vertical asymptote is use your graphing calculator, look at the table. Plug in numbers, don't plug in h, because that would cause you to divide by 0. You can't plug in h, but you can plug in a number close to h, approach h. Right? So if h is 5, try 4.99999. Or try 5.0001. Plug in a number very, very close to h on each side. And see if, as you do that, does your graph all of a sudden take off to infinity or negative infinity? That's how you can tell if you have a vertical asymptote. So if you found the domain are the values you don't use are the vertical asymptotes. So there's no extra work to do once you have the domain. There's only one exception to that. Okay, so you want to find your domain, find the ones that don't work. And those most likely are going to be your vertical asymptotes. unless you had a common factor. So if you had a problem like this, and I asked you the domain, hopefully you would say it's all real numbers except 3 and -4. And this says that if the numerator and the denominator don't have a common factor, then 3 and -4 would be vertical asymptotes. Well, I agree that -4, if you were to type this in on the calculator, -4 is going to be a vertical asymptote. 3 is not. 3 causes you to divide by 0. It's still not in the domain. But does anybody remember what happens on the graph if you have a common factor in the top and the bottom? Something you can't see on the graph because it's very small. Yeah?
A hole.
A hole. Okay? If you have a common factor in the top and in the bottom, then you get a hole in the graph. You don't get a vertical asymptote. So if I did this, now I would say that there are vertical asymptotes at 3 and -4, because those are the zeros of the denominator. If I did this, now I would say that there is a vertical asymptote at -4. At 3, there's a hole. Okay? This doesn't happen a lot, that you get common factors. It would have to be set up just right for that to happen. Okay, any question on that? All right, let's try this one. First of all, look at the numerator and look at the denominator. Are there any common factors in this case? Jake? No, you don't have an x minus 2 in the top. So you don't have to worry about anything special. So all we have to do here is find the values that make the denominator 0. And what would you plug in to make the denominator 0? Chris?
+2.
+2. So the equation of the vertical asymptote is x equals 2. Right. About this one. What would be the equation of the vertical asymptote here? Jake?
Would be -3.
And how would you write the whole equation?
Oh, x equals -3.
X equals -3. Perfect. What if I did this? What would be the equation of the vertical asymptote now? Yeah?
X equals -3.
X equals -3. How about now? Yeah?
X equals -3.
Right, I'm trying to point out that it doesn't matter if you add or subtract something at the end. All that matters when you're finding the vertical asymptote is right there. What is the value that makes the denominator 0? And it is -3. All right, let's start graphing that one. All right, let's look at this one. So this is going to have to do with a transformation. So let me first write down kind of a template that shows you what the transformations are. And let's see if this matches up with my template. Okay. This is what you want to look for when it asks you to describe how one graph can be obtained from the other. It has to be set up like this. A number. Actually, let's write this. A number, plus or minus, a number, over, a number with an x, plus or minus a number. Each one of those boxes will do something. when you add or subtract inside the denominator, that's a horizontal shift, and that's always the first thing you would list. This is still in the denominator, so it's horizontal, but it's multiplication. That's a horizontal stretch. This is multiplication. It's basically multiplication. It's in the top. That's a vertical stretch. This is adding and subtracting again, just like the first one, but it's outside the fraction. So anyone have a guess which way this is going to shift the function? When you add or subtract a number on the end of it? Yep.
Up and down.
That's going to be an up or a down. And the numbers that I put with them is always the order you would list them in. Now, in box 2 and box 3, you could have a negative. Does anybody remember what happens if the number you're stretching by is a negative? It causes the graph to do something. Yep.
Reflection across
Yes.
both sides.
Yep, it'll cause it to reflect. Which axis depends on which one we're talking about. If you put a negative in box 2, that's a horizontal reflection. That causes a reflection like this. That's a horizontal reflection. If you put a negative in box 3, that's a vertical reflection. That would cause something like this to look like that. That's vertical. So if box 2 or box 3 is a negative, you get a reflection. So now, look at the problem that I gave you. Does this look like what I just wrote? Does it have a single number in the top and then like a plus or a minus with a number at the end outside the fraction? No, this doesn't match this. So we're not going to be able to describe until we make that look like that. How do we make this look like that? Divide it out, just like we learned in the last chapter. Now, you can do long division or synthetic, but I would do synthetic on this one because it's x minus a number. Okay, so let's divide it out and write down what we got. What would go on the outside if we divide these out? Yep. 5. And then you'd have, it's going to be the shortest synthetic division we've probably ever done. 2, negative 13. Okay, let's do it up. Bring down the 2. 5 times 2, Matt, what's that going to give me? And negative 13 plus 10?
Negative 3.
Negative 3. Okay, let's write our answer. Remember how you can write your answer in long division. Think back to like middle school long division. Quotient plus remainder over divided. There's my quotient. In this case, it's minus my remainder over, what was I originally dividing by? X minus 5. That, in green, is the same thing as that in black. Now, if you look at it, it does fit that pattern. They put this box in the front, but that's fine. It's still the same thing. So let's put our horizontal asymptote. Tell me what happens to this box in black as x approaches infinity. What number are we going to get very close to in that box? Okay? 2. As x approaches infinity, this is going to disappear, what I just circled. You're going to have 3 divided by a huge number. It's basically going to disappear. So you're going to have 2 minus a very, very, very small number. So it's basically going to approach 2. Now vertical asymptote. Look for the 0 of the denominator. What's the 0 of the denominator here? Chris?
Positive 5.
5. Do I have an x minus 5 in the top?
No.
Nope, then it's not a whole. It is an asymptote. So we got that. We got that. And now the last thing is the transformations. I'll give you a hint. There are 1, and if it helps, think of it this way. It's exactly the same thing, minus or plus a negative, but there are 1, 2, 3, 4 transformations. What number would we focus on first? Yeah?
5.
The 5. Good. The 5 is a horizontal shift, and it's a minus. Does anyone remember, what way does a minus move when it's horizontal? Be careful. It's a minus, so it... Yep. Bailey? Yeah.
To the right.
It does move to the right. So shift 5 right. Okay, good. That's the first one. What's the next number that I would focus on here? Well, normally you'd look for box 2, but there's nothing in box 2. It's a 1. So you can ignore box 2. So what is in box 3 in this case? Just the number. Nothing else. Just the number part of it. Yep.
3.
It's a 3. And that's a vertical stretch by a factor of 3. Now, that box also has a negative, and that does something else. What did we just say the negative is going to do?
Reflect.
Reflect over which way? Or what type of reflection? It's in the vertical box, so it's a vertical reflection. Yep. Which is reflecting over the x-axis. So we dealt with the 5, the 3, the negative. The last thing is this 2, and it's a positive. They put it in front. That's okay. What is that 2 going to do? Yep.
Shift up.
Good. With vertical, positive is up, negative is down. It's just like you would expect. Shift up 2. Okay. So there's one thing we didn't get to. That's fine. We'll do it tomorrow. So I'm going to take one question off the and it's a mixture problem. So if it wasn't on the test, I would probably skip it, but it is going to be on the test, so we'll do it tomorrow. So on 207, 8, 9, and 10, those are graphing and finding intersects. And then on page 222, 3 through 7 odd, 11 through 21 odd, 23, 31, 37, and 38. You can skip 48 because that's the one we didn't get to. We'll do 48 in class tomorrow.